Well, welcome to a special field edition of the Radio Physics and Electronics video blog. It's 4th of July weekend and it's very hot. And we just had our patio built. Still a few finishing touches left. But it kind of inspired me to work outside today. And it had been few weeks, certainly longer, between videos than I like to do. So I've been thinking about antennas a lot lately, and I decided to throw something together and investigate how it works. And this is what happened. So this is actually difficult to get in the entire shot. It's so wide. This is a loop antenna that I have just thrown together, pretty much literally. You can see the admittedly chintzy construction. And like I said, I threw this together in a day, less than a day. Took me the morning to do this with hand tools, and I used stock that was left over from my workbench, actually, and so there you go. This is 24 gauge magnet wire, enameled magnet wire, and I put slots in the wood here, enough for, I guess, 9 or 10 pieces of wire. Right now I've only got 4 pieces of wire, 4 loops wrapped around. But just thought it would be interesting to do a quick little informal video here of how I've done it and the results. So I'm going to try to do this without a tripod. Always a dubious thing. So I've got here one of the ubiquitous, 10 to 360, 380 picofarad variable capacitors. And with the DE5000 LCR meter, I was able to measure the inductance of the loop of the larger antenna as a function of number of loops. And it compared not too terribly well with the online calculators that you see. And I probably want to try to figure that out from a physics perspective at some point, which means doing more math. But that's not today. So, what else do I have here? I've got an MFJ antenna analyzer, and I'll show you how I'm going to use that in a moment. But first, let me get a shot set up so that I can demonstrate the actual value of the inductance here, measuring it from the LCR meter. So, hang on. What I've done, and as I said, this is a complete hack. This is a proof of concept. This is not an antenna ready for prime time DXing. But I've just got, alligator clips over here, and they're running to the DE5000, and with 4 loops. The dimensions of this antenna are basically 6 feet square. So it's, 36 square feet of area. That works out to, you measure it to be about 110 microhenries. Okay? And again, I've just got clips here attaching the variable capacitor So let's next bring the antenna analyzer into the circuit. And let's just experimentally determine what the range of the resonance points are for the smallest amount and then the largest amount of capacity. So hold on. We'll see how this goes before I knock the camera over. But here I'm just going to sweep the frequency, and I'm starting around 570 kilohertz, and I'm going up in frequency. And you see the impedance, X right here, is going down. It's about 220 ohms, 160 ohms, 84 ohms, and you see we're very quickly getting to a null. And there we are at just a couple ohms, and that's at 720 megahertz. All right? I'm sorry, kilohertz. 0.72 megahertz is 720 kilohertz. All right. So now let us get a close-up of my hand there. Let's put the capacitor all the way at the other end. So this has the least capacitance now. And we're going to now tune this up in frequency and see where we are. So it's greater than 1 megahertz. It's a 2. Let's go downward. And you see we just saw a very sharp null there. Right around 1.8 megahertz. It's very, very sharp. Just make sure there's nothing else. No. Okay, so 720 to around 1.8 megahertz is the range of this. It's really touchy up at 1.8 megahertz. And so there you go. Let's demonstrate this now very quickly by tuning in a radio station that demonstrates just how much EM that this loop picks out of the air. So hold on. All right, well, our in the field video just got a very quick rain shower, so it was a scramble to get the LCR meter and the video camera and little radio out of harm's way during the deluge, which successfully did. And the rain shower moved on, and now it's just phenomenally uncomfortable with the heat and humidity again. So I like the air-conditioned shop. All right, well, what I'm going to do here is I've found a radio station at 930 kilohertz, and got the little Texon PL380 here. And as I push, as I orient the radio in the direction of the station, that is to say, so that the ferrite antenna inside it's got the axis pointed towards the station, and then if I go perpendicular to that, I don't get any signal. There's a big pulse of noise right there. But you can see that I'm getting readings between 15 and 20 for noise. I'm getting no signal to noise ratio. And that's how it is. So I'm about 30 feet, maybe closer to 50 feet from the loop antenna, which I've brought to resonance. And I'm just going to start walking. So right now I've got the axis of the ferrite perpendicular to the plane of the loop. And I don't know if it comes through on the microphone of the camera, but you can just hear a little bit of signal in the background. And I'm walking now kind of diagonally towards the loop. I'm going to turn around 180 degrees so that maybe we can better see the, okay. So the noise is now 20 or above, and you can just kind of hear the picket fencing a little bit. Now I'm going to move towards the loop. Actually, I'm going to turn around 180 degrees because that just did not help anything. Right, so now I've got 24, and I can hear a little bit of music in the background. And there's a signal-to-noise ratio of around 3 or 4. Now I'm just going to move directly toward the loop. And we've got about 24 dB microvolts, I guess, dB mu on the Tecsun, and a signal-to-noise ratio of between 4 and 8. Now I'm just moving straight towards the loop, okay? Here's the loop. 23. Now I'm going to move around 180 degrees. 28, 33, and look at the signal-to-noise ratio shoot up. I'm maybe 2 feet away from the loop. And now I've got 45 for the signal strength and a signal-to-noise ratio of about 16, 17, 19, 18. And this is right on the axis of the loop. Okay? So that is that's an illustration of where we are. Just going to move off the axis there so that we don't infringe on any copyrights. All right, and as I said, this is a proof of concept. This is just hacked together with my alligator clips and plywood and, you know, very hastily constructed loop. The construction of this is only meant as a proof of concept. So there will be, you know, lots of stray capacitance in the alligators, and you can notice, if I just walk around here a bit, that I've really done an ugly job of bringing the feed point for the loop all the way down. I wrap them around a couple of screws that I've got in here, and then I just, you know, kind of bring them forward down to this contraption. So there'll be lots of stray inductance, there'll be lots of stray capacitance. This is in no way shielded, so there'll be lots of capacitance between the distributed capacitance between the loop here and the surface. And not to mention that, you know, I've got this large half of a parallel plate capacitor essentially in this metal table right here. But nonetheless, there it is. Very quick demonstration of something very quickly thrown together. We can get lots of signal out of the noise, and I'm really looking forward to trying this out at night and seeing how that goes and experimenting a bit with this. I was going to, before I had to very rapidly get the electronics out of the rainstorm, I was going to show where I had clipped in parallel a 100 picofarad capacitor across the variable capacitor, and then you can shift the range of resonant frequencies for the loop. But Mother Nature had other ideas, and it probably doesn't merit demonstrating. I think you'll probably take it on faith that that works. Okay, again, just a short video. I'm not going to do a lot of editing on this. It is what it is, but I wanted to throw together something and get it up, get it onto the channel. All right, hope you've enjoyed this. If so, please give it a thumbs up below. And as always, thanks for watching.